let's talk about oxidation reduction reactions. So oxidation reduction reactions, or it's also called redox reactions. So oxidation reduction reactions, they involve a transfer of electrons from one compound to another compound, or one atom to another atom. For example, think about an ionic compound. Let's say we have potassium. Let's say this is its one electron, right? And it reacts with fluorine, all right? Fluorine has 1, 2, 3, 4, 5, 6, 7 electrons. And this potassium, because both of these atoms want a full valence shell, what happens is the potassium transfers its electron to the fluorine. When something loses an electron, that thing is being oxidized. So when something loses an electron, it's being oxidized. And when something is gaining an electron, that thing is being reduced. So obviously, when this thing combines together, it's going to form potassium fluoride. And you can see how the potassium has a +1 charge, while the fluorine has a -1 charge. So the charges balance each other out in this reaction. Now, how are you supposed to kind of find out whether a reaction is an oxidation reduction reaction? Because normally, like the example I showed you before, you can easily find out if something's an oxidation reduction reaction if it's an ionic compound. But what if it involves covalent compounds? Then it's a little bit more tricky. And let's get into it. So first of all, the oxidation number for any single element is 0, alright? So just for a single element by itself, in this case oxygen, right? This is the only element, right? So the oxidation number would be +0. It has no oxidation number. Oxidation number of a single gold atom, that would just be +0. Oxidation number of hydrogen gas, this would just be +0, okay? So any element by itself has an oxidation number of nothing. No oxidation number. Alright. Now here are a couple of rules. And from the periodic table, this might be pretty self-explanatory. So you have your periodic table. I'm not going to draw out the whole thing, but Alright, let's just say this is group 1. Group 1. This is group 2. Alright. Now, group 1 elements, all of them form +1 charges. Doesn't matter which group 1 element is. All of them form +1 oxidation states. Group 2 elements, they like to form +2 oxidation states, right? They like to form +2 oxidation states. Fluorine. Fluorine usually forms -1 oxidation. It has a -1 oxidation number. Oxygen, most of the time, like 99% of the time, it has a -2 oxidation number. Alright? So, kind of from this information, I didn't give you all the information of the periodic table. You have that on your own, but you can use this information to actually assign oxidation states in your compound, right? So let's take a look at our first compound, KClO3. K, this is a group 1 element, right? And what do we say about group 1 elements? They have a +1 oxidation number, which means K has a +1 charge. We also know that oxygen, remember, has a -2 charge. So it has a -2 charge. Alright. Now you can see that overall, the molecule itself is neutral, right? So it's kind of like in an ionic compound where the positive charges and the negative charges, they balance each other out, right? So in this compound, the positive one, right, plus -2 times 3, that's -6. So 1 minus 6, plus the oxidation number of chlorine, we don't know that. Chlorine has multiple oxidation numbers, which means we have to solve for it, alright? So the reason why a lot of elements on the periodic table, have a lot of oxidation numbers is because usually in these like redox reactions, right, it can form different ions, which means you have to solve for the specific ion that it forms, right? So yeah, just to repeat the steps again. Potassium has a +1 charge. Oxygen has a -2 charge. But because there's 3 oxygens, right? 3 times -2, it's -6. And we don't know the oxidation state of chlorine. Let's call that X. And we know that since this molecule overall is neutral, it has to add up to 0. All these charges have to balance each other out to create this neutral molecule. So solving for X, this is just some pretty simple math. So simplify this, 1 minus 6, that's -5, x minus 5 equals 0, x equals 5, and you get that chlorine has an oxidation state of +5 in this compound. Let's look at KCl. We know that K has a +1 charge, once again. And Cl, well, we know that this whole molecule is neutral, which means the positive charges have to balance out the negative charges. So right now we have a positive charge here, and we don't know the oxidation number of chlorine, but we can set this equation equal to 0 because this compound overall is neutral. And solving for X, we get that chlorine has a -1 charge in this case. So you can see how the oxidation number of chlorine has decreased in this reaction. And obviously, remember what I said about single elements? Single elements have a +0 charge. So you can see oxygen went from an oxidation state of -2 in the beginning to +0 at the end. With a +0 charge. And you can see that chlorine went from a +5 charge to a -1 charge. So my question to you is, which element is being oxidized and which element is being reduced? Well, chlorine went from a positive to a negative, right? When you go from a positive to a negative number, you must be gaining electrons, right? Because imagine if you have something like, let's say chlorine, for example, hypothetically, had a +3 charge. If you give this chlorine atom an electron, it's going to form a chlorine atom with the oxidation number of a +2 charge, because 3 plus -1 gives us 2. So if the oxidation number decreases in value, that means that you're gaining electrons, which means this thing is being reduced. And that means the oxygen is being oxidized. Therefore, this is an oxidation reduction reaction.